So any questions on this topic in programming? So what you need to do is to find the f, a, b, a, eq, b, eq, and x, x, small m, and x, capital M, and then call the program to find the solution. And another special example or special form of constraint optimization problem is the quadratic programming problem. And it is quite similar to the case in linear programming problems. Besides this one, we have a quadratic term here. If we remove this term, it gives us standard linear programming problem. So this is another form of special form of constraint optimization problem. And sometimes this topic is also useful. And how can we solve this problem? If we can find the H matrix, then we can solve it easily, because we know how to find the F and AB, AEQ, or something like that. So we should have H first, and then we can solve the problem. And the problem can be solved by calling a quad program. And the difference is we have to add H matrix here. So we compare it with the linear programming problem. And here is an example. This is a standard quadratic programming problem. So how can we convert this one into a standard form? There is no problem on the constant. We have talked about it earlier. Constant it is still the same as the one we deal with linear programming problems. But what about the objective function? What we need to do is to extend it first. x1 squared, we have x2 squared, x3 squared, x4 squared, minus 2 times x1, 4 times x2, 6 times x3, 8 times x4. And then we should have 1, 4, 9, 16. We can easily find the S vector from it, that's no problem. And what about the H matrix? This kind of representation can be actually denoted like this. The quadratic form, the matrix description to it should be written like this. Any problem? This one should be correct. If we multiply these two together, and suppose x here is a column vector. So these two are equivalent. But you must be very careful. This one is not H. So you must be very careful in solving quadratic programming problems here. Let's check the standard form. We have one path there. So you must be very careful. If you use H like this, you will get incorrect results. So what you have to do is to do it like this. So this one is H. So in this time, you must be very careful with it. So this is H, this is F, and what about this? In the standard form, we didn't talk about the constants. Actually, you can just delete it, because constant in the objective function does not affect the final result of addition. You can just remove it. So we can solve this problem easily. And we have H matrix here, And we have f vector, actually it should be minus. This one should be with the minus sign. So there is a constant.
So H is going to be the same matrix all the time, just to become.
For this example it is, but for other example, H might be asymmetrical for certain problems. X1. For instance, if you have a term like this, you may write it like this: 1, 1, 2, 1. You can rewrite the matrix. You can also write it as asymmetrical matrix. Oh, sorry, I'm not quite sure with it. It should be okay. And right here, the command here is correct. We have minus signs. So we can specify all the matrices and then call program. And finally, we should get the result. And these are the final optimized variables, and this is the objective function. And you might be surprised to see that this one is negative, because we have removed the 30, the constant, from the original objective function. After optimization, we have to add it back. So the final one should be positive for this particular problem. So these are the solutions to quadratic